start with the chapter Current Electricity. We've already studied about charges in electrostatics, right? Now when these charges are set in motion, we get what is called current. So what is electric current? Electric current which is donated by I is equals to dq by dt, which is the rate of charge flowing through a particular conductor. Right? Now, if I denote J as the current density, then I can write I as J into A. What is current density? Current density is current per unit cross-sectional area. Next we come to electric potential. Electric potential is the reason why charges flow from one point to the other. It is denoted by V, and also V by L, or electric potential per unit length of the conductor, is also called electric field. Electric field causes a force due to which the charges flow from one point to the other. So if there is no potential difference between 2 points, then charges will not flow and there will be no electric current. We'll be studying about drift velocity now. So drift velocity is denoted by Vd. Now when there is no electric field, then what happens is the energy of the electrons or the charges will be equal to their total kinetic energy, right? So from this equation I can write that Vrms, or root mean square velocity, is equals to 3kT by m, where k is the Stefan-Boltzmann constant and T is the temperature. Right, and m is the mass. Now, this is when no electric field is present. Now, if electric field is present, then what will happen? The drift velocity of the electrons or the charges will be denoted by E into E, small e into tau upon m. Here, the symbols are important. E is the magnitude of the electric field. Small e is 1.6 into 10 raised by minus 19 coulomb, which is the charge on a single electron, right? This is minus 19. And tau is the mean time between two collisions. And m is the mass. So this is the formula for the drift velocity when electric field is present. In this case, I can write the current as N into E into A into Vd. How? Vd is the drift velocity, A is the area. So drift velocity has the units meter per second, the area of units are meter square. Now this is meter cube per second. So this is current flowing in a unit volume per second, charge flowing in a unit volume per second. Right, so charge flowing in 1 meter cube per second, right? So if I multiply this by n, which is nothing but the electronic density. Electronic density means the number of electrons which are present per unit volume. N is electronic density, which is number of electrons upon the volume. So this equation is important, NEAVD. This must be remembered. Now, to find the current density is current flowing per unit area. So I'll divide this equation by A, so I'll get J as NEVD. Yeah. Let's move on to the next important topic, fourth topic here, which is conductivity and resistivity. So yeah, we obtained in the earlier equation that J is equals to NEVD. Now if I substitute Vd from the above equation, from this equation, I will get N into E square tau upon m into the electric field. Now this is a constant for a particular scenario, right? And tau we mentioned is the mean time between two collisions. Now this constant is represented by sigma, which is called the conductivity, sigma E. So sigma is the conductivity. Now these formulae must be remembered because obviously deriving them will be very time taking, and we obviously want to avoid wasting time. So yeah, this is conductivity. If I denote rho by rho as resistivity, we know that resistivity is 1 upon conductivity. The next topic that we study will be resistance. Now resistance is a concept which will occur very often in this chapter. Now in the last topic, that's conductivity and resistivity, I derived this equation J is equals to sigma E, where J is the current density, E is the electric field, and sigma is the conductivity. Now in place of J I can write I by A, which is current per unit area, sigma, in place of E I can write V by L, which is potential per unit length. So if I solve this equation, I can get V is equals to rho L by A into I. Rho L by A I substitute by R, which is called the resistance. So I get the equation V is equals to I into R, which is potential is equals to current into resistance, and where resistance is equals to rho L by A, where rho is the resistivity, L is the length of the conductor, and A is the cross-sectional area. These two formulae are very important. They'll be used in almost each and every question from current electricity. Now we move on to the dependence of resistance on temperature. Resistance as a function of temperature. So for resistivity, I can write rho is equals to rho naught 1 plus alpha T minus T naught. Right? Where alpha is positive for metals and alpha is negative for semiconductors. What does this mean? That if alpha is positive, as temperature will increase, resistivity will increase. Right? So for metals, resistivity or resistance are directly proportional to temperature, and for semiconductors, resistivity and resistance both are inversely proportional to temperature. This is very important. So I can write the resistance as rho L by A. So if I substitute, I will get RT is equals to R naught into 1 plus alpha T minus T naught. Right? Again, where alpha is positive for metals and negative for semiconductors. Right. So yeah, now we will see the series and parallel combinations of resistances. Now this is again extremely important. In series, when the resistance are connected end to end, they are said to be connected in series. That is, the current passing through each of them is same. The potential through each of them is different, which depends on their resistance. Right. I can convert this into this simpler circuit where this single resistance will have the resistance of R effective, where here R effective will be nothing but the summation of all the resistances in series. When I come to parallel combinations, when resistors are connected in parallel, they are connected like this, right? So potential across each of them is same because they are connected across the same ends, but the current varies, right? The current varies. Here I1, I2 and I3. The current varies, but the potential remains same. Here current remains same. Right, so here R effective, or the effective resistance of three resistors in parallel, R1, R2, R3, is given by, the relation between them is this: 1 upon R effective is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Right. So yeah, these two formulae must be remembered. They're going to be parts of almost each and every question in current electricity. Right. So moving on, we now come to cells and batteries. Right. For any circuit, they are also extremely important. So cells are represented by this symbol, plus, minus. This is important to remember. And a combination of cells is called a battery. Right. Now, we'll talk about the internal resistance of a battery or a cell. Internal resistance of a cell. So let me denote this circuit. Okay, in cells and batteries, we talk about their EMF, which is the work done in passing a charge, a unit charge from from one end of the battery to the other end. This is given by the open, which means that when the battery is connected to open circuit, then the work done required or the potential across it will give us the EMF. It is an important concept. Now, when I talk about a battery or a cell, it has some internal resistance also, which are denoted by small r. Now, if I take this entire portion, if I talk about only this part of the cell, then it has an EMF of, let's say, V0, right? But due to its internal resistance, the effective EMF decreases, right? Okay. So yeah, this concept is again important. Then now, or I would say in this case, V effective. Okay? Effective potential will be less than the EMF of the cell due to the internal resistance of the cell. Right. Now, just like we can have combinations of resistors in series or parallel, there can be combinations of batteries as well. So let's discuss that. Ninth topic here is battery combinations. First, we'll talk about series combination. Now, in series combination, the equivalent EMF is N times E. The potential just gets added, and the internal resistance, like in general resistances get added in series, the same is going to happen in this case. Right. Now, when you're adding the EMFs, just remember that if a battery or a cell is reversed, then just take the negative of the EMF. That's it. That's the sign convention we're going to follow. And when batteries are connected in parallel, then E equivalent is nothing but E because the potential remains same across each, right? Because they're connected in parallel like this. This is the sinusoidal combination. Okay? And R equivalent, the internal resistance, the combination of the internal resistance will be R by N if there are N batteries connected in parallel.